Beatrice Pozzetti, who is currently at the University of Bologna, right? And the oldest university in Italy, am I right?
That's correct.
Yes. And who is going to talk about this very trendy topic of high-rank Teichmüller spaces.
Okay, so thank you very much for the introduction, and thank you, Cornelia, for having me here. I think, and for dragging me here, like for insisting very much that I'm here. It's great. I mean, I've arrived 2 days ago, and it's already been fantastic. And I'm really happy of being here. And I don't know most of you, so that's something else that makes me happy, because I'm very happy of meeting new people and like learn new things and interact with the different. With many of you. The fact that I don't know you means that it's very hard for me to judge what your background is and what you know and what you don't. So please feel free to interrupt me at any point. I'm happier to have a conversation than to just lecture to myself and to my head. Okay? This being said, I want to tell you a little bit about this very high-rank Teichmüller spaces, which is part of a very active field that's really quickly developing in the past 20 years. And eventually I will try to tell you some ideas from some joint work of mine, but I'll specify that when we get there. So like my plan for today is to first tell you what are these objects, like give a definition, and then tell you how do I think about them, why I think that they're interesting, and eventually why they exist. And hopefully by then you will be first surprised that they exist, and then like happy that they exist. But let's see if this is the case, okay? So the definition is that, I will talk about high-rank Teichmüller space. I write HTS for them, higher-rank Teichmüller spaces. And HTSs are connected components of character varieties Let me write chi for a character variety, which will be the quotient of the set of homomorphisms from a group gamma that I'm going to specify in a bit to another group G up to G conjugation that only consist of injective or conjugacy classes of injective homomorphisms with discrete image. And here, this is the object I want to tell you about, the story about today. And here, I need to tell you a little bit more. Here, gamma is the fundamental group of a higher genus surface. I'll draw a genus 2, but any G. So the topological surface of genus at least 2. And G is a simple, non-compact Lie group. And you should think of SLNR, the group of n by n invertible matrices, or SO PQ. But actually, any Lie group, in some cases, algebraic groups, so really group of matrices, which is simple as a group, a topological group, which has a smooth structure, is simple, and is non-compact, will do and will play a role in this theory. Some of them will play a role in this theory. Okay? So that's the kind of object I want to tell you about today. And like the plan for my talk is to tell you why I think that injective with discrete image is an interesting subset of this character variety. And then maybe why Teichmüller, why higher rank Teichmüller spaces, so why this name. And then I want to tell you that they exist. And this, in part, is due to my work with collaborators, my recent work with collaborators. Any questions or complaints so far? So So I didn't really like connect the component. Like let me talk a little bit about character varieties first. And so, in a sense, something that I liked of this theory or this part of mathematics is that it's really at the crossroad of different areas. So I will tell you in a minute that character varieties are really algebraic or semi-algebraic objects, so come maybe from real algebraic geometry or are of interest in algebraic geometry or real algebraic geometry. I will tell you that this injective with discrete image is really differential geometric, interesting in the sense of differential geometry or metric spaces. And there is more coming to it. There is really analytic techniques building in this theory. There are geometric group theoretic techniques building in this theory and low-dimensional topology helping in. And these has also algebraic application, cluster algebras, such things. So that's why, like, I mean, this area is very rich nowadays. But let me tell you something about character varieties. Maybe let's go this one. So character varieties. So in general, like so up there, my chi is like I'm looking at group homomorphisms from a finitely generated group, this fundamental group of the surface, into a topological group. That's a Lie group, and it's off like this simplicity is telling me that if under mild assumptions, so like if it's center free, for example, this is really a group of matrices from linear algebra. And in particular as a semi-algebraic structure or algebraic structure. And so gamma, my fundamental group, is a finitely generated group generated by 2G elements, A1, AG, B1, BG, where the product of AI, BI vanishes. So it has a number of generators and one single relation. This tells me that gamma G is really a subset of G to the 2G, right? So so like to tell you what's an homomorphism from this group, I need to tell you the image of all these 2G generators. And to get the homomorphism, I need this relation to be satisfied. So my homomorphisms, my representation variety, is a subset of G to the 2G defined by algebraic relations. Which is that the product of these matrices that I'm prescribing here needs to be the identity. And so it's naturally an algebraic set if the group was algebraic. And now taking the quotient of G action by conjugation still can be done in this real algebraic world. And so that the quotient is, so the GAT quotient, so like the quotient by conjugation is itself a nice, possibly singular real semi-algebraic variety. And so has a lot of nice structure. It's not always smooth, but has a big smooth locus. And it's an interesting variety on its own, arising naturally from group theory. Okay, so this is the GAT quotient. This is my character variety chi that I was looking at it. And so this is of interest maybe from algebraic geometry, this manifold. It can be very complicated, like there is in general, like the topology is hard to describe, but still has some nice structure in most places. On the other hand, I don't care about all possible homomorphisms. So inside this character variety, I have what I call chi discrete and injective. So that the set of homomorphisms that are injective, this is a generic condition, because not being injective meaning that some extra relation holds. This cuts out a codimensional locus. And but being discrete is a complicated notion that's not really algebraic. And my claim is that this is a subset of interest for a differential geometric viewpoint, from differential geometry, and I'm going to say a few more words about this in a second, but typically is closed but very fractal. So typically the set of inside this character variety, which has a nice structure, the set of injective homomorphism in discrete image is typically a closed set with fractal boundary. And so it in itself does not inherit some nice structure from the structure, the group structure. That's one reason why having components is good, because having components has the same good structure that the ambient space has. It's also semi-algebraic set, and it's also a very nice parameter space that's a nice manifold that parameterizes interesting objects. So let me say a few words on why I think that this is subject of interest from differential geometry. So that's, or metric geometry. So the point of this discrete and injective, the way in which I think of this injective representation with discrete image is as nice actions on symmetric spaces. So to bring this up, the group G was a group from linear algebra, but I really want to think these Lie groups are a group from differential geometry, meaning that I think of G as the isometry group of the quotient of G by its maximal compact, a component of the isometry, where this quotient is a simply connected Riemannian manifold of non-positive curvature So this is the symmetric space. Which is beautiful because it's non-positively curved, but there's a very big group acting. It acts transitively and more than transitively. And there's a very intricate geometry that mixes flat and hyperbolic features in general. So like, for example, some examples of this I want to keep in mind is that if G is PSL2R, then the symmetric space is the hyperbolic plane. Mixed surface, simply connected, complete surface of curvature -1, constant curvature -1. But in general, for example, if G is PSLNR, then the symmetric space is the space of positive definite symmetric matrices of determinant 1, that some people call SPD. And the interesting feature of, so like for example, P3 is a five-dimensional manifold, and in these five-dimensional manifolds, which is topologically evolved, I see both totally geodesic copies of H2 of different kinds, but also totally geodesic flat subspaces. So, totally geodesic subspaces isometric to R2. So I really mix hyperbolic geometry and flat geometry in an interesting pattern that encodes like projective geometry in some way, and also really mixes these two. For example, every vector is contained in a maximal copy of R2, and all of these are conjugate. All these R2s are conjugated by the group action in a strong way, and there is a lot of interesting branching and negatively curved phenomena that arise in this nice geometry. Okay? So geometry of symmetric space is old and beautiful, and if I really think of G as the isometry of its own symmetric space, the set of injective homomorphism with discrete image is set of interesting actions. Right? So if rho gamma to G is injective and as discrete image, then this is the same as saying that the action of gamma through rho on G mod K is faithful and properly discontinuous. Which means that this gives rise to a quotient manifold, which is a locally symmetric space, which is an interesting, which is a manifold which is locally modeled on this beautiful geometry, but has non-trivial topology coming from the fundamental group. So this is a interesting infinite volume, typically infinite volume Riemannian manifold, which is homotopy equivalent to a surface, so that's why it has infinite volume, but still has a very interesting geometry that depends and sees a lot of this point here. And in particular, when I have a higher rank Teichmüller space, I have such connected component parametrizes. It's an interesting manifold that parametrizes whose points correspond to interesting manifolds. Because when I have this point in this high rank Teichmüller space, which is a connected component of the character variety that only consists of injective homomorphism with discrete image, every point corresponds to one such symmetric space, which is well defined up to isometry. You should think of this as something that's kind of like a surface, but has much bigger and much more complicated geometry. Huh? Any questions on this? And okay, again, like the fact that I have components tells me that the parameter space of these nice manifolds has a lot of structure, as a semi-algebraic structure, and also can be attacked with analytic techniques like Higgs bundles to study them, or like both more algebraic and analytic techniques to study them. Also, another word for why Teichmüller spaces. So, if there are no questions on this, so like the reason why this is called these are called high rank Teichmüller spaces, or why it's maybe not such a bad idea to call them this way, is because if I take G to be PSL2R again, which I thought of as the isometry of H2, then the subset of the character variety considering injective homomorphism with discrete image is nothing but the set of marked hyperbolic structures on my topological surface, SG. Gamma was the fundamental group of my surface. So looking at injective homomorphism with discrete image is the same as, like then the quotient by H2 will be a compact hyperbolic surface, and I'm looking at marked compact hyperbolic structure on my topological surface, which through uniformization is the same as the Teichmüller space of SG, which is the Riemann surface structures on this surface. And there is a lot of like Teichmüller theory studies really geometric properties of these hyperbolic metric on surfaces. And there is a lot of research and a lot of nice results about this study of these specific class of manifolds, of curvature manifolds. But in this case, it's not a higher rank, it's the classical Teichmüller theory, because this is really negatively curved. And in this case, the action is co-compact. So the action of the group, it's the only case in which the action of gamma can be co-compact on H2, and will be co-compact if it's injective as discrete image. And this says that, okay, I can believe that if I start from a nice hyperbolic structure and I deform, I will forever be nice and discrete and injective. But in general, the cohomological dimension of this group is much smaller than the dimension of this space where I'm acting. So there is no reason to believe that I cannot perturb my action to become very complicated, like I have dense orbit, or so why should these still be nice forever, no matter how far I deploy? And like the surprising fact is that these high-rank Teichmüller spaces really exist, despite one might think that the group gamma is too small with respect to dimensional symmetric space for this to happen. And like maybe the theorem that I want to discuss with you today was joint work with Jonas Beider, Olivier Guichard, François Labourie, and Anna Wienert, which says that there exist higher-rank Teichmüller spaces, so nice connected components of these character varieties for the following classes of groups. Which are if G is split, if G is Romian, if G is isogenous to SO PQ, or if G has type F4, so as a restricted group system of type F4. So in these four classes, there exist high-rank Teichmüller spaces, and conjecturally, this is O. And this is open only for few exceptional groups. So for the non-experts, Lie groups are classified and are really the groups that you learn in linear algebra. Comes from form on vector spaces, plus a few exceptional groups that have been classified. And so what we prove is that, so okay, part of this was much older than this. Like in the case of split group, these are Hitching components. Which have been known and studied for maybe 30 years now, or 20 years. And for Romian Lie groups, these were older and have been studied for maybe 20 years. They are maximal. And the existence in these two cases is really new and due to our work. The fact that there are connected components that only consist of injective homomorphism with discrete image. So, yeah, any questions on this? So what I hope of doing in the second half of my talk is to tell you a little bit. Yeah. Yeah. So like I'm assuming here that the surface is closed. This group here for G arbitrary at least 2. There are analog theories for open surfaces, but then the fundamental group is free, so the character variety is connected if the group is connected. There are variations in which you can like prescribe some mild boundary holonomy, disconnecting the character variety, and there is a similar theory that works out also for open surfaces. But that's like a different story. More questions or comments? Yeah.
So you're proving there is a kinetic component. This is presumably not unique, and if there are different kinetic components, do they somehow relate to each other?
Yeah. So that's a very good question. It depends a lot on the group. So like the point is that the only way I know how to understand really connected components of character varieties is passing through X bundles. Like there are some topological invariants that tell some components apart, but the only way I know to say that this is really the number of components is through X bundles. There I get more classical objects like holomorphic bundles of Riemann surfaces with holomorphic data that has been classified in the past. I can give really the count of And the fact this is conjecture, this is all really comes from there. So that many groups have connected character variety. If the character variety is connected, for example, adjoint complex groups that connect character varieties, if that's the case, there is no hope of having one of these because I have the trivial representation there. So that's all. And this conjecture is really like that. That like in most cases, like any component of the character variety has some representation whose image is contained as compact subgroup. And these are exceptional components that should not be there, are there because they were looking at real Lie groups. And for split, it's only one if the group is adjoint, and there's some different lifts that are like essentially the same one as the other, if not. For example, the Teichmüller space, I mean, it's not entirely true. It's two components that are essentially one the same, like the correct orientation and wrong orientation. With lifting problems and like orientation preserving and reversing problems. In these cases, it's not true. So there are many components that are really different, one from each other. So like both the maximal case and the SOPQ, there are some components that come from the being split, that are balls and are smooth, and that's a nice property. And there are some other components that are not smooth of these high rank Teichmüller spaces, and maybe some phenomena in between.
So can you see that through the symmetric spaces that you get from that correspondence, or?
Yes and no, in part. Like depends on, yeah. I mean, it's like most of these can be told apart through topological invariance that you can read through the action of the symmetric space in some complicated way. A posteriori. A priori, not really. More questions or comments? So what should I erase? So like that, the reason why I want to tell you a little bit about our proof of this result is because it really brings in a lot of like classical study of hyperbolic structures on surfaces with different ideas coming from symmetric spaces, or maybe the boundary of symmetric spaces that gives a little bit an idea of something that goes into this field. And indeed, like the way we prove this theorem is to really building a lot of theory of understanding of these symmetric spaces, which is why I like this proof. And that's why I wanted to share it with you, or give you some hints of some ideas on how this works. So I was telling you at some point earlier that one should not expect that these exist, because this group is too small to really see all the geometry of the symmetric space. And so one should expect that everything can collapse eventually using the extra space that you have. The special feature, however, of these groups, despite their very high cohomological dimension, they're very big dimensional, that makes them amenable to be seen everywhere, I mean, fully by these small groups that are fundamental groups of surfaces, is that they have some boundary structure that really reminds the group, the fundamental group of a surface. Yeah, so maybe what's the reason? So I want to tell you something about the theory developed by Olivier Guichard and Anna Wienert, that's theta positivity. Which is morally the reason why these groups are really of dimension 2 in some sense, that allows for these components to exist. So the idea is that one reason why the Teichmüller space up there is closed, I mean it's a full connected component, can be traced down to the fact that the action is co-compact, but can also be traced down from the fact that you have a circle at infinity. Yeah, so like I think here, like here I want to think, I mean, have you thinking about S1, so like we're saying that we're looking at PSL2R, which is the isometry of H2, which I have drawn like the upper half plane, but I can also think really as the unit disk in some model. And I have S1, which I think of as the boundary of H2. And when I fix a point in this component, so a geometric action of the fundamental group of the surface on this disk, I also act on this boundary, this set of equivalence classes of rays, it's RP1, but there I act in a very complicated way, in a very ergodic way. And so I want you to think about this boundary of H2, which in more theoretic terms I can think of G mod P, like the only compact quotient of PSL2R that exists in this case. And this circle has the interesting property of having a partial cyclic ordering. So if I look at triples, I have two connected components, positively oriented and negatively oriented. And this is rigidifying a lot. And given two hyperbolic structures as G on the surface, I have a unique equivariant boundary map. So here I have the circle of the universal covering of the first hyperbolic structure, on which I act through rho 1. And here I have the other circle on which I act through rho 2. And there exists a unique equivariant map phi between these two actions. And this equivariant map, which extends any diffeomorphism between the two surfaces, is uniquely prescribed and has the property that is monotone. Meaning that if I had 3 points that were positively oriented, the image is still going to be positively oriented. And monotone maps are very nice. Like monotone maps from the circle to the circle have very little room to play. And so this is a strong feature that will persist if I perturb the action, and will keep this being a connected component of the set of actions. And this is one reason why you should believe that it accounts for the Teichmüller space of being closed among the set of actions. So if I perturb, like it's open and closed in such action. And so the idea is that the idea of Olivier Richard and Levinard is that there are some classes of groups, like these ones, for which I don't really have a compact quotient with a total cyclic ordering, but there is a nice partial cyclic ordering. Yeah, so in general, definition, weird. We say that the pair G theta admits a theta positive structure if there exists a distinguished set of transverse triples G1 P theta that has a semi-group structure. And you should think of this as a partial cyclic ordering. Okay, so let me unpack this a bit. So now, like I told you up here about the circle as its cyclic ordering, the circle as the only compact portion of PSL2R and as the boundary at infinity. For these high rank groups, the boundary at infinity of the symmetric space is more complicated, and there are different kinds of compact quotients of G. They all arise as strata in the boundary, and these are the flag manifolds. And so I want to have a pair, I want to have a group G that admits a flag manifold, so you should really think of this G mod P theta as at infinity in the symmetric space. And I want there to be able to say that some triples are positively oriented. And these triples behave as triples in the boundary of the circle. So the idea is really that when you have something like this, you can define that representation from my, so remember I wanted to look at representation from the fundamental group gamma of a surface into G is theta positive if it admits a monotone map, a monotone equivalent map from S1, which is the boundary of gamma in any chosen hyperbolic structure, to G mod p theta. Now, this definition, this is a bit of a lie. That's why I didn't give this as a definition. There is a lot of Lie theory that goes behind in defining this properly, and there are problems due to the fact that this doesn't pass well to finite covers. So finite covers of the flag manifold might have this partial cyclic ordering, some might not. But still, the point is really that on this circle, I had the notion of monotonicity, which was forbidding me from folding back and doing complicated behaviors. And these pairs have some Lie algebraic property that does the same for me. That tells me that I can understand this representation through a circle that I see at infinity, which is prevented from folding back by some Lie theory that's hidden under the rug. Okay, so that's okay. So and really the idea is that I want to thinking about representation themselves for their action, their nice, interesting geometric action on the space is too complicated. But I can look at the trace they leave at infinity. This is uniquely determined. It doesn't depend on any choice, of any orbits or anything. And there are some pairs for which this has better properties. And actually, this circle at infinity will be as smooth as it gets. So it's going to be always a Lipschitz submanifold of this flag manifold, and there's lots of extra structure coming from this partial cyclic order. And the theorem that I should write up here is that, write it down here. The theorem is a classification of Richard-Minard that these are the groups that admit a theta positive structure. So this happens. So there exists p theta precisely in these cases. There exists a subgroup p theta such that g p theta has a positive structure precisely for the groups in this list. There are these four classes, and in each case, I should tell you what is p theta, and for those of you who know, if G is split, I should choose p theta to be the set of all roots, the minimal parabolic, and in these other three cases, I should choose the long roots, which is one parabolic that exists for all this. Yes. Okay. And now, what we actually prove in the theorem, I wanted to, I promised that. So I wanted to introduce this to give you an idea of what's a property of why this list. So what's the special feature of these kind of groups? And then I will, of course, need if I want to prove something like this, I will need much more, to know much more about this theta positivity. To remember is just that there is some big compact homogeneous G space that has some parts that behaves a little bit like a circle with its cyclic orientation. And what we actually prove in, so like the actual result is that theta positive representations form connected components. And the point is that it's not so hard as an exercise to show that if I have a theta positive representation, so I have this nice boundary map, I have this nice subset of this compact space at infinity, where I act as in the boundary of the disk, then I have to be injective. And I have to be faithful. I have to be injective and I have to be a discrete image. Why? Because that can be seen from how I act on triples in the circle. So like I cannot have anything in the center, in the kernel of the representation, because that acts non-trivially up there and will act trivially here. So being theta positive means that it's an injective and discrete image. And so what we prove is that like, the idea is that theta positive representations are open and closed. And there are two parts, and they are very different one from each other. And I want to tell you something about why they are closed. So 10 more minutes, Rob. There are two parts, like the theorem is that the positive representations are open and closed. The fact they are open is older. Theta positive reps are open. The openness relies on dynamics. This is come from the theory of one-off representations, which is an active and beautiful theory that I will not have time to talk about today, but can be attacked. So this openness can be attacked through either dynamical techniques or understanding the geometry of symmetric spaces. But that I will not say anything more than this today. The theorem that we actually proved is that they are closed. And this really builds on some Teichmüller theory, so some understanding of the geometry of these symmetric spaces, and that's what I want to tell you about, because it links a bit back to what I started talking about at the beginning. Any questions on this? So the fact that they are closed builds on two results that are inspired from geometric properties of hyperbolic structures on surfaces. Maybe that's part. I think I didn't have all the parts on my board, but there's part 4 I rank. Teichmüller theory. So the first result that we prove is a color lemma, which is key in closeness. So again, this was this was proven before for split groups by for SLNR actually by Li Zhang, for summer mission group by me with Mark Burger, and so we have the general version now with new ideas and techniques. What we prove is that is this property. So I have rho from gamma to G, theta positive representation. And now I take two elements, gamma and beta, in my fundamental group of the surface. Maybe that's the worst possible board to write on, sorry. And like I want them, so remember gamma was the fundamental group of a surface, and I want them to intersect in the surface. That's a topological assumption on these two group elements. Maybe gamma is this one, and delta is this one. So like gamma, beta, and gamma, where intersection of gamma and beta is at least 1. Then we show that e to the L of gamma minus 1 times e to the L of beta minus 1 is bigger or equal than 1. Where L is the translation length on the symmetric space of rho of gamma. Okay, so why? So this is inspired, as I was saying, from Teichmüller theory. Let me tell you what this means, and try to bring this up. Okay, so what does this mean? This means that so rho of gamma, rho was the representation from gamma to the isometric group of this non-positively curved manifold, and so I have like this rho of gamma acts on this symmetric space and translates by something. This is the minimal amount it translates for any point in the symmetric space. So if rho of gamma is a fixed point, which a priori could have, then E, L of gamma, the translation length would be 0, so this would be 0. So this in particular says that no element in the image of my representation has a fixed point. And in general, this is telling me that if this translates very, very little, then any other element that crosses it has to translate very, very long, because I want to keep this inequality. So if this translates very little, this goes to 0, and so I have to compensate with the other, going to infinity in a logarithmic way. And this is really inspired from the hyperbolic color lemma that says that if I have this short curve in a hyperbolic surface, then this has a long embedded color neighborhood. So everything that crosses it has to be long. And in general, this would be like a consequence of the Margulis lemma if I had an intersection point. Because the Margulis lemma tells you in general that for action on symmetric spaces, no two elements can translate little in some point. But the problem is that here, the symmetric space is so big that even if the two guys were intersecting in this surface, there is no reason why they should intersect in the space. So this is a surprising fact that, in a sense, says that these actions on these high-dimensional manifolds still remember a lot of the topology of the surface. Actually, this result is not quite good enough for what we want. Are there questions on this? So this is, I think, a nice geometric corollary of what we prove. What we need to get closeness is a strengthening of this, in which I can replace this by lambda I of rho of gamma over lambda I plus 1 of rho of gamma, so some eigenvalue gap for some suitable set of gaps that depends on theta. This is a stronger version than having this inequality that's actually helping us get our hands on limits of positive representations. But already the geometric corollary, I think it's, I like already the geometric corollary. That's the weakening of what we have. Any questions or comments on this? Now let me see one other a second bit that goes in this proof. Which lets me tell you a little bit more about interesting features of symmetric spaces. So like I was telling you that the symmetric spaces, G mod K, as a natural Riemannian, is a Riemannian, I can think of it as a Riemannian manifolds on which G acts by isometry. But there is more. So there are admits many different twin-square metrics for which G acts by isometry. Admits twin-square metrics for which G acts by isometry. And the point is that choosing different metrics, like coarsely they are all the same. Up to constants, they are all comparable, these metrics, because they share the same isometric group, so they share the same large scale geometry. But different metrics detect different fine properties of actions and different fine properties of these representations. And like the second result that builds, the second weakening of a result that builds in our proof of closeness for this representation is a length shortening under surgery, which is again bringing some low-dimensional topology idea in this high-dimensional setting. And the way in which I want to state it today is that there are appropriate twin-square distances which I can describe explicitly but not without any background and not in the next 2 minutes, for which if, again, I was on a surface, and in my surface, I had a loop that was topologically self-intersecting. And so I have one loop, I can pull it tight in any hyperbolic structure, and I see a self-intersection. This means I can write gamma as concatenation of two paths, gamma 1 and gamma 2, that starts from this base point. Gamma 2. If I choose a hyperbolic metric, and I look, like I chose the shortest geodesic representative of this loop, this has this self-intersection, I can cut it up here and get two different loops. And of course they are shorter because they can now move away from this self-intersection. And what we prove is that the same holds in this setting, which the length of gamma 1 after gamma 2, so the length of my big group is bigger or equal than the, strictly bigger actually, the length of gamma 1 plus the length of gamma 2. For an appropriate set of pincer distances that I can describe. That depends on my set theta. And again, this is something that says that even if my action was now taking place in this high-dimensional space in which the shortest representative, even if it exists, has no self-intersection anymore, because there is enough room and there is no reason why it passes through itself, and it does not actually pass through itself. Nevertheless, cutting it makes it shorter. And this is false for general character. And maybe just one word on to finishing this is that this is again as a weakening of the statement that we actually need to prove closeness, so this comes from understanding both of these facts actually. Come from understanding cross ratios on G mod P theta. So like if you have done some hyperbolic geometry as up there, you know that a lot of the hyperbolic lengths can be encoded in the projective cross ratio RP1 on the boundary. And in order to prove this result and that result, we understand cross ratios on these high-dimensional compact manifolds, these stack manifolds, and different cross ratios to serve different purposes, and show, for example, that some cross ratios are positive, which gives this result, and understand the relation between different cross ratios, which let us read these algebra. And I guess that my time is over, so I'll stop here and thank you for your attention.
Questions?
See, the theorem is at higher rank, G mod K.
Yeah. So the idea is that the theorem, as the other theorem, is like I'm in the setting in which this is for any theta positive representation. So like the setting is I have these groups here, like this is all the no for G equal SL2R, PSL2R, so there's arbitrary product plane. That was my motivation for doing this. But this is interesting for the other cases in which the group is high dimensional and has rank at least 2, because the only group in this list that has rank 1 is PSL2R. And so here is all a higher rank phenomenon, and like the assumption that I said but not right is that I have rho from gamma to G, a theta positive representation, which is not here anymore, but assumed that G has a theta positive structure, and I have this nice positive boundary map. Under this assumption, I know that the action on the symmetric space resembles the action on the hyperbolic plane in these concrete terms, among others.
What about compactifying these high-dimensional spaces?
Yes, there are lots of interesting ways of compactifying them. So one way of compactifying them that I like is using this semi-algebraic structure that is built in the fact that they are component. So there are semi-algebraic varieties, and with Mark Burger, Sandra Yotz, and Amparo, we have been studying the compactification coming from real algebraic geometry, which is this real spectrum compactification. And this links very well with actions on asymptotic cones of the symmetric space. So like we have this natural compactification coming from real algebraic geometry, whose boundary points really parameterize the suitable equivalence classes of actions on buildings that are limits of actions coming from actual representation. This is one of them, one way of compactifying. You can also compactify it recording the length function. This is like Thurston compactification. There is a lot of work in that. And of course, you get different compactifications, choosing different ways of measuring length. There are some ways that really are translation length on the symmetric space, which are the ways I like the best. But there are other more analytic ways that have been studied in which you take, for example, minimal surfaces and you look at the induced length from a minimal surface. And also in that case, there is a lot of progress on understanding these compactifications, how it behaves.